Hello, oceanography students. The topic for this week is atmospheric circulation, which essentially means how the air circulates around our planet. Okay, so why are we going to study atmosphere in marine science or oceanography class? One, the processes that affect the atmosphere also affect the ocean. The ocean influences atmospheric weather, and each process on Earth is tied together and sensitive to change. So even though our focus in this class is on the ocean is also influenced by land and also by the atmosphere. So in the next week's lectures, we're going to talk about ocean circulation. In order to understand ocean circulation patterns, we need to understand atmospheric circulation patterns, because the atmosphere, the circulation patterns, and the heating of our planet is ultimately what is driving the ocean circulation. So if we don't understand atmospheric circulation, we can't fully understand ocean circulation either. Okay, so let's look at what our atmosphere is made up of. So our atmosphere has water vapor in it, of course. It's about 78% nitrogen and 21% oxygen, with smaller amounts of argon, ozone, carbon dioxide, and various dusts and trace elements. So the majority of our atmosphere is actually nitrogen, and then we have a little bit of oxygen, which is what we need for respiration and for basically changing our food into chemical energy. But the important one that we want to consider for this lecture is water vapor. So water in the gas form in our atmosphere. That's going to be really important. Okay, so as we move away from our planet and into the atmosphere, we can look at how that temperature changes, and based on those temperature changes, we have different layers in our atmosphere. So in this picture here, we have altitude on the y-axis. We have temperature on the x-axis. Okay, and so you have this red line that is showing you how the temperature changes as you go from Earth, down here where we stand, all the way up into the sky. All right, so the bottom layer is called the troposphere. Then you have the stratosphere. Then you have the ozone layer, and then you have the mesosphere. So I want you to look at this red line and notice that as we go up into our atmosphere, the temperature decreases. Okay, so it gets colder as you go up, and then we see that the temperature is actually going back and increasing again in the stratosphere. So that change, the lowering and then the raising, that change creates what's called the tropopause. And the tropopause is basically a barrier between the troposphere, which is the layer where we exist, and the stratosphere up here. So as you go from Earth up into our atmosphere, the air pressure decreases. Okay, so the really important thing for us understanding atmospheric circulation is this tropopause and the troposphere, because this is where all of our weather is created, in the troposphere. And essentially, if you have air that's rising up, that tropopause acts as a barrier so that the air doesn't keep on rising. Instead, it rises up and then it spreads out when it runs into the tropopause. Okay, so the troposphere is where we're going to focus our attention today. Okay, so imagine if you have a parcel of air that is close to land, and it's heated up because the sun hits the land, that changes into heat, and that heat warms the air. So we have this warm parcel of air as which decreases its density. Right? Warm air is less dense than cold air is. Okay. So again, warm air is less dense than cold air is. So when air gets warmed, it will rise. So we see the air parcel rises up, and then remember from the previous image, the temperature is colder in the upper atmosphere. So the temperature of it decreases, the pressure decreases, and this parcel of air expands. Then, as it gets denser, it sinks back down, and as it sinks back down, it compresses and it warms. Okay, so that's essentially what happens with the circulation around our planet. There are some places where air warms and it rises, and there are some places where cold air in the upper atmosphere is sinking. Okay, so like I said, water vapor is very important for circulation patterns. So when the sea surface is heated up, or when any body of water is heated, or moisture on land is heated, the water evaporates, which means that it goes from a liquid to a gas. So it's basically putting water vapor into the atmosphere when that happens. But it also depends on how much water vapor is already in the air and the temperature of the air as well. So at a given temperature, water vapor is in equilibrium with the water surface. So essentially what that means is whether or not the water is going to evaporate depends on the given temperature and also on how much water is already in the air. Less water vapor in the air means more water will evaporate, okay? Warmer air can also hold more moisture than cold air can. I'm sure that you have experienced this. If you put a wet towel or a piece of wet clothing outside to dry in the summertime, it dries really quickly, right? The water evaporates from your towel and your towel dries. If you do the same thing in the winter when it's cold out, even if the air is very dry, it's still not going to evaporate very easily, okay? So warmer air can hold more moisture than cold air can. Adding water vapor to the atmosphere actually makes the air less dense, and adding water vapor then, because it makes the air less dense, that causes the air at that location to rise. So the air and the water vapor, where the water vapor is added, rises at that location. Okay, and I know that that might sound a little bit counterintuitive if you have been to some place where it's very humid, because lots of times people will say that the air is thick where it's humid, and that's not really true. It's actually the opposite. When there is more water vapor in the air is actually less dense. So if the surface of the ocean is evaporated, that means that the air gets water vapor added to it. That means that that air is now less dense, and therefore at that location where the water vapor has been added, the air will rise. Now, whether or not evaporation occurs obviously depends on the temperature and depends on how much water vapor is already there, but since it depends on the temperature, obviously the sun is going to be important here, right? So the sun is responsible for changing air temperatures and causing the water to evaporate. So how does the sun's energy vary around the globe? So our Earth is round, right? Therefore, the amount of sunlight that hits our planet is not equal at all parts of the planet. Instead, the majority of the sun is directed at the equator, and as you go farther and farther away from the equator to the north or to the south, more of the sunlight is actually reflected. So up here, about 40% of sunlight is reflected. And also, once you get up to the North Pole or to the South Pole, you also have something else there. You have ice instead of water. Ice has a higher albedo, which means it's more reflective, and so the sun will reflect off of it even more than it will off of land or than it will off of water, okay? So generally, you're getting the majority of sun is directed right at the equator, and as you go farther and farther away, you get less and less energy from the sun. And to show that, your book has a nice little image that shows what happens when you shine a flashlight on a flat surface. So imagine, I don't know where you're sitting, but I'm sure there must be a table somewhere where you are. Imagine if you have a flashlight and you shine that flashlight directly down on your table, and you look at the light that is the area that's illuminated by your flashlight. that area is a small area and it should be fairly bright. Whereas if you take that flashlight and then you put it at an angle, now you look at the area on your table that's illuminated and there's a bigger area that's illuminated. However, it doesn't seem as bright. And if you take that at even more of an angle, you are illuminating even more of that area on your table, but any given point on that in that lit up area actually is less lit up than when you just shined it directly down. Okay, so shining directly down, you have the most intensity of the light, whereas when you shine it at an angle, that light is spread out, and therefore any given location has less intensity of light. So basically, this one right here, where you're shining it directly down on it, that would be like what the equator experiences. And up here, where you're shining it at an angle, that would be like what you're experiencing up towards the poles. Okay, so, and as you go farther away from the equator, basically the angle is causing it to spread out over a greater area, which means that any given spot within that area is going to get less solar radiation than a given spot within the area around the equator. Okay, now we also see changes seasonally in radiation patterns. Okay, so here we have basically the position of the Earth in relation to the Sun over the course of a year. All right, so if we start right here, September 23rd, since we're right around that time now, what this is showing us is that the Sun is hitting right at the equator. The angle of the Earth, oh, I should back up, I didn't tell you this yet. So Earth doesn't just sit straight up and down in relation to the Sun. Instead, it's on a tilt of about 23.5 degrees. Therefore, the way that the Sun is hitting is not always the same. It depends on the positioning of the Earth in relation to the Sun. So at the autumnal equinox, which happens on September 23rd in the fall, we have the Sun directed exactly at the equator, okay, at 0 degrees latitude. Now, as we progress into the next season, as we progress into the winter, on December 22nd, now you'll see that the northern hemisphere up here is now angled away from the Sun. And the Sun's energy is hitting directly at about 23.5 degrees south, which is called the Tropic of Capricorn. So when that happens, the northern hemisphere is going to experience their shortest day of the year, okay, because we are getting the least direct hit from the Sun. As the year progresses and we get into the vernal equinox, or March 21st, the Earth is back in a position so that the Sun is hitting it directly at the equator again, okay? So what that means is that we have an equal time, our day is equal to our night on March 21st. As we progress farther into the year, we get to summer solstice, which is June 21st. Now the Earth is positioned in a way that the northern hemisphere is angled towards the Sun. So the Sun is directed right at about 23.5 degrees north. And that angle there, that latitude, is called the Tropic of Cancer. Okay, so essentially over the course of a year, and so this is when the northern hemisphere experiences its longest day. The opposite would be true at this time for the southern hemisphere. The southern hemisphere would be experiencing its shortest day of the year. Okay, so basically, as the Earth progresses around the Sun over the course of a year, the direction that the Sun is hitting, the angle that the Sun is hitting, goes between 23.5 degrees north down to 23.5 degrees south. And that basically, that is a year, essentially. Okay, so as it goes back and forth, it hits the equator, and then it goes south, and then it comes back to the equator. Now what happens at the North Pole or at the South Pole during this time is that if in the Northern Hemisphere summer, when the sun is angled at 23.5 degrees north, because of the shape of our planet and the tilt of the planet, the North Pole is going to experience 24 hours of sunlight. Because even as the Earth is rotating around, right, over the course of a day, it never leaves the sun. It's never angled away from the sun, and therefore it has 24 hours of day. The opposite would be true for the southern hemisphere down here. As the Earth rotates around, the southern hemisphere is always angled away from the sun. So over the course of the day, it's always dark. And then the opposite would happen with our northern hemisphere winter, where the sun is now angled at 23.5 degrees south. Now the southern hemisphere is experiencing their summer, and the South Pole is going to get 24 hours of sunlight because it's always in the sun's rays, whereas the North Pole is going to experience 24 hours of darkness. So what this means is that Earth's surface is not heated equally. Essentially, the sun's energy is directed between 23.5 degrees north and 23.5 degrees south, just along the equator, right? And so the farther you get from the equator, the colder it gets. Now, that then creates a pressure and a density difference that then drives the atmospheric circulation, which then drives ocean circulation. Okay, so at the equator, you would have a net gain of heat, which would create low pressure and cause the air to rise at the equator. At the poles, you would get a net loss of heat. That cold then creates high pressure, and air will sink at the high pressure. Okay, so luckily, our equator and our North Pole are not in isolation from one another. Instead, you have heat that gets transferred from the equator up to the North Pole and cold air that gets transferred back down. Okay, therefore, we're not seeing a net increase of temperature at the equator or a net decrease of temperature at the poles, right? We're seeing a fairly stable Earth environment. And that's because of the circulation patterns of both the air and the water. So heat is transferred through airflow in this way. So we're going to follow the path of a parcel of air as it is heated near Earth's surface. Okay, so in this image here, this green is representing Earth's surface, and the light blue is representing the troposphere, and then this little dashed line up here is representing the tropopause. Okay, so remember that as you go from land up into our atmosphere, the temperature gradually gets colder. Okay, so in our image here, this area right here is heated by the sun. So the sun is directing heat at the land here. That warms up the air and also causes evaporation to occur of water. And therefore, the air is warmed. It rises because it decreases in density, and we end up having a low pressure zone get created. That moist air rises up into where it is colder. So essentially, the moist air cools, and that cold air can't hold as much moisture as the warm air could, right? So remember, warm air can hold more moisture. Cold air can't hold that moisture. So as the air gets colder, that moisture in the air, that water vapor, condenses and then drops back down as rain. Okay, so generally where you have low pressure, you also have rainy conditions. Okay, so now remember what I said about the tropopause up here. The tropopause acts as a barrier. So that air that rose up, instead of continuing to rise, it spreads out along the top of the troposphere, just below the tropopause. in either direction. Okay, so it's moving away now, but it's moving away not along the land, it's moving away up in the upper atmosphere. Now this air that is moving away, it's already lost its moisture. It doesn't have water vapor in it anymore. That water vapor was released as rain. So now it's up in the upper part of the troposphere, which is cold. So that air gradually gets colder and colder until it eventually gets dense enough that it sinks back down. So that's what's shown right here is the air that's sinking back down. Where air is sinking, you have high pressure zone that gets created. So in a low pressure zone, molecules are spaced farther apart. In a high pressure zone, the molecules are packed in, right? So I always think of it as if you go to a concert and when you're up at the front of the stage, that's like the high pressure area, and when you're farther away, there are fewer people there, so that's a low pressure area. Now, if you stay in the high pressure area too long, if you're like me and you're slightly claustrophobic, you are going to want to get away from that area. So air acts the same way. It always wants to move from high pressure to low pressure. So once this air sinks and it gets onto the surface of the land and you have high pressure, it's going to move away from that area. It's going to spread out in both directions and move towards the low pressure. And what this creates is continuously circulating air. Where it rises, it spreads out, it sinks, and it comes back down. You have a continuous cycle, continuous circle, or a cell, if you will. So this is what would happen at the poles, right? Air sinking. And this is what happens at the equator, air rising, right? Places where it's warm, air rises. Places where it's cold, air sinks, right? Cold air, more dense, sinks. Warm air, less dense, rise. Okay, so that's what that would look like around our planet. Along the equator where it's hot, we have air rising. And at the poles where it's cold, we have air sinking, right? And so once that air sinks, it moves back towards the low pressure area, right? So we have low pressure here, we have high pressure here. Air is always going to want to move from high pressure to low pressure. So in this way, we have continuously circulating air around our planet. But it doesn't work that simply because the Earth rotates. And what that creates is something called the Coriolis effect. Coriolis effect is going to deflect the movement of air around our planet. Okay, so something that's in motion, for example air or water, will be deflected to the right of its motion in the northern hemisphere and to the left of its motion in the southern hemisphere. And along the equator, the Coriolis effect is 0, which means it's not deflected in either direction. And the farther you go from the equator, the greater the Coriolis effect is. Okay, so the next video that you're going to watch is a video that demonstrates Coriolis effect. Okay, if you have any questions, please post them under the weekly discussion.